Evaluating logarithmic expressions without using a calculator. Now, listen, I know that there are calculators that have log buttons with different bases. In fact, the calculator I suggested for the course has the button where you can change the base on log. Casio calculators typically do. TI calculators are hit or miss. Regardless, it's really good to be able to do these without a calculator because they explain and solidify the mechanics of logarithms for you. So while yes, you can use your calculator to do problems like these, I really suggest doing these manually to make sure that you truly understand what's happening with logarithms, because logarithms, they work differently than what we're used to. If you haven't seen logarithms before, they're uncomfortable at first. So when we're evaluating logarithmic expressions without using a calculator, we're thinking about what it means to be a logarithm. In particular, when I look at this guy here, log base 4 of 64, I'm asking myself the question, what do I need to raise 4 to in order to make it 64? Right? 4 raised to what power is equal to 64? And interestingly enough, if I had done this as log base 4 of 64 equals whatever, think about what the loop-de-loo would do here. Loop-de-loo. It would be 4 raised to the whatever equals 64. Now, you might not know off the top of your head what 4 needs to be raised to make 64. You can mess around with it in your calculator. The answer is that 4 cubed is 64. 4 cubed is 64. So log base 4 of 64 is 3. Log base 5 of 1 over 25. This is a really good moment for us to revisit negative exponents really quickly, which I will do. Make some room in here, I guess. Over here is fine. So if I say 7 squared is 49, you're probably going to say, yep, that sounds about right. I'm pretty confident about that. When we have a negative exponent, it brings us down to the denominator. So if we have 7 to the negative 1, this is 1 over 7. And if we have 7 raised to the negative 2, this is 1 over 7 squared. So this is 1 over 49. So anytime you see something like 1 over something that you know the value of, let's like 125, this is equal to 5 to the negative 3, because 5 cubed is 125. So if 125 is in the denominator, that means that the exponent on 5 would be a negative 3. Okay. 125 is 5 cubed. 1 over 125 is 5 to the negative 3. So just that quick revisit with those negative exponents. So let's go ahead and make this a loop-de-loop problem. So we start at the base 5. So 5 raised to what power gives us 1 over 25? Well, I know that 25 is 5 squared. And since it's in the denominator, it should be negative. So 5 to the negative 2 is equal to 1 over 25. Okay. 1 over 36. This is 6 to the negative 2. 1 over 16. This is 4 to the negative 2. Anyway, the answer to this one is negative 2. Log of 100. When there's no base written, we are base 10. So we're asking ourselves, what is this equal to? So 10 raised to what power gives us 100? 10 raised to what power gives us 100? Well, the answer is 2. 10 squared gives us 100. 10 squared gives us 100. So the answer is 2. 2 is what went into that box. Log of 100 is 2. Okay, you can see how this game works. The game doesn't get much different than this. Ooh. Start at the base, across the equals, back again. 7 raised to what power gives us 1? 7 raised to what power gives us 1? Make it into a box. Well, the answer is that the only thing that we can raise any number to in order to make it 1, besides 1 itself, which is always going to be 1, is 0. If we raise something to the 0th power, it is equal to 1. Anything to the 0 is 1, except for 0 itself. And that's except 0 to the 0, which is indeterminate. Indeterminate. So if you have a number raised to the 0th power, it is 1. So log base 7 of 1 is equal to 0. The power that you need to raise 7 to in order to make it into 1 is 0. So then here's kind of a weird one. This is a trick question. Log base 2 of 0 is what? Start at the base, across the equals, back again. What exponent do we need to raise 2 to in order to make it 0? 2 to what power gives you 0? Keeping in mind, we already covered what happens if you make 0 the exponent. 2 to the 0 is 1, so don't tell me it's 0. It can't be 0. That gives you 1. And the more positive we make our exponent, like if I do 2 to the 7th, which I don't know off the top of my head. Oops, I just did 2 to the 77th, which my calculator said no to. So like if you make the exponent big, it's going to make this number big. 2 to the 7th is 128. 2 to the negative 7th is 1 over 28, 1 over 128, but as a decimal, 0.0078125. If you make it more negative, like 2 to the, let's see, negative 20, 0. There's 6 zeros here, I think. 1, 2, 3, 4, 5, 6, 9, 5, 3, 6, 7. These are getting very close to 0. And you might be able to put in a big enough number that your calculator essentially thinks the answer is 0. For example, if I put 2 to the negative 1,000 into my calculator, it says 0, but it's not actually 0. It's just, it thinks it's 0 because it's so small. There is no number that you can raise 2 to in order to make it 0. Thinking of what 2 to the negative power even means, is that you have that many copies of 2 in the denominator, right? This right here is 2 to the negative 4. You have 4 copies of 2 in the denominator. So no amount of copies of 2 in the denominator is going to change the fact that there's a 1 in the numerator. That 1 in the numerator is going to prohibit this whole thing from ever being 0. It can't happen. It's impossible. There is no solution. This is not a real number. And as it turns out, we just simply cannot take log of 0. That's what ends up happening. We can't take log of 0. Doesn't matter the base. All right. So that's evaluating logs without a calculator. I'll see you in the next video. We'll talk about graphing. So excited. See you then. Bye.